Welcome back, guys. So today let's review what we learned in the last lecture. We learned about electric field and electric field lines, right? So let's review a couple of key things that we learned. So electric field lines, direction of electric field is tangent to electric field lines. Density of electric field lines gives the strength of electric field at that point. Sign convention: electric field lines begins from positive charge and ends at negative charges. And there is also physical constraint. Since the electric field lines point in the direction of the field, no two field lines can intersect in space. Okay, so we talk about that because we cannot have two different direction for electric field at any point in space. Okay, so that was the property of electric field lines. We also, drew electric field lines for several configuration of charge. Some of the charges were positive charge. The field line, it just begins from the positive charge, and you see you have this, arrow going outward, right? So, and negative charge is the same thing, but then now the arrow changes and it just goes back. So it was basically positive was going out like that, right? Field lines. If you have a negative, then it would be just negative, then the line would be coming in to the negative, should be coming in, sorry, that one coming in. Okay, so like this line is not proper, so let me redraw this. So it will be coming in like this. Okay, so that was for this charge configuration. We also saw field lines for two charges, right? Two positive charges of equal magnitude, and it looked like this, right? So positive charge, both have positive charge, but then in the middle they kind of, the field lines from two charges, they kind of go away, right? So we have this space here because these are positive charge, and positive charge are supposed to repel, right? So the field lines, they go away from each other. Okay, so we looked at that. We also looked at the electric field lines for dipole. So if you recall, dipole is what makes a dipole. So basically, if we have two charges of equal magnitude but opposite sign, then it forms a dipole, right? So we have two charges here, one is positive, one is negative, and then this distribution forms a dipole. So the field line begins from the positive, ends at negative, and we have this configuration, and the field line looks like this. Okay, so that was the field lines produced by some configuration of charges. We also learned about electric dipoles. So if these two charges, positive charge and negative charge, are separated by distance d here, then we can write, dipole, electric dipole. Equation for electric dipole is P. This is usually lowercase p. It's a vector quantity. It points from negative charge to positive charge. So the direction of electric dipole is opposite to that of electric field. Okay, electric dipole P is given as QD. Okay, so that was the equation for electric dipole. Oh, this is also important. So we said that what would happen if we place electric dipole in uniform electric field. We talk about that this, dipole would experience torque, right? Basically, it will rotate, so there will be torque. Okay. So we said some of the molecules have a dipole, for example, like water molecule, right? Because of the separation of the positive charge and negative charge due to the oxygen atom and hydrogen to hydrogen atom, there is a separation of charge, and that forms that polarizes the molecule basically. So water molecule is it's an example of a dipole.